In Chapter 10, we learned that amines can be synthesized by treating an alkyl halide with ammonia or another amine. But we also learned that because these reactions tend to produce a mixture of different amines, synthesizing amines that way is generally not very useful synthetically. So one way around this problem is to carry out something called a reductive amination, which is seen here of a ketone or an aldehyde. So we start with this ketone or aldehyde functional group, right? And we see an example here. And first, the aldehyde, in this example, it's an aldehyde, is treated with an amine to produce an imine. So I just want to remind you, an imine is that carbon double bonded to the nitrogen there. And we learned about that in the previous section. And so this is really similar. Then we have sodium borohydride is added. And what sodium borohydride does here is it reduces the imine to an amine, right? And so notice that the nitrogen of the amine, which is right here, right, is in the exact location of the oxygen of the carbonyl carbon, right? So that carbonyl oxygen is basically replaced with a nitrogen atom. In the example that's shown here, particularly, a primary amine was used to produce a secondary amine. So what we're talking about here is there's a primary amine here, and now we've produced a secondary amine here, proceeding through an imine intermediate. So that's how we would describe this reaction. If ammonia, right, which is NH3, were used instead, an imine would still be produced as the intermediate, but the product would be a primary amine. Okay, and so there would be some differences there depending on the reagents that you use. Now, in this equation, sodium borohydride isn't added until after the amine formation has come to completion. And amine formation takes place under slightly acidic conditions, which would neutralize the sodium borohydride. And so that's why we do that. And this takes time and it's kind of a pain. So scientists look for kind of a solution to this. So a clever solution is to use sodium borohydride cyanide instead. And so when we look at this particular reaction, right, and we react it with the NH here, there are several steps, right, that we get, and we go to the imine here. Oh, I put hydrogens there. Those are not hydrogens. They're just CH3 groups, sorry. And so that would be a positive charge because it's got 4 bonds. Comes here, and we still have that kind of sulfur, rest of that sulfur group there, and the halide. Okay, so we have that, and so what sodium borohydride, sorry, that is not sodium borohydride cyanide does is it is going to come in here, and the hydride part is going to come in and attack that amine carbon, right? Because we still have this reactive center there, and then these electrons are going to jump up there, okay? And this is called an iminium ion, right? Because we have an amine with an I, but now it's an ion. And so when we do this, it produces I want to draw my bonds a little better here. Okay, so let's go down here. There we go. So I want to point out, I'm always kind of looking back at the previous one, and so sometimes I do get a little lost looking back and forth. But what I was doing there is I was counting my carbons. That's a great double check that you need to continue to do as you do this. All right, so this hydride here, right, comes from this complex here. And so what happens, the reason this is really helpful is this cyanide here makes the electron withdrawing group less basic. So we don't have that same problem where there's a side reaction in an acidic environment. So because the CN group makes it less basic, it allows for it to remain intact under these mildly acidic reaction conditions and continue to react. Okay, so that's one of the parts of organic chemistry research is if there's a part of a reaction that is not as effective or takes a lot of time, we're always looking for solutions to make reactions go faster or make the workups a lot easier, because just honestly, time is money. And so these would be more likely to be used in industry and larger syntheses as well. So that's why that's an important part of organic research. Now, we're going to look at a Wolff-Kishner reaction. This is a Wolff-Kishner reduction. And what we see here is a carbonyl group of a ketone or an aldehyde is converted to a methylene group. Now, I want to remind you a methylene group is just a CH2 group here, right? So that's just another synonym for that. I want you to notice this is under mildly acidic conditions. That's why we see acetic acid here. And then it's followed by heating in the presence of a strong base. And sometimes under the reaction conditions, you'll see a temperature like we see here. And then ethyl cyclopropane is produced. Now, so basically with this particular reaction, we again are taking this carbonyl carbon and reducing it to a CH2 group. Now, we are going to look at this mechanism, and one of the things that I want you to kind of transition to a little bit, and so we'll do a little bit more of this through the second semester screencast, is I want you to be able to look at a mechanism and read it. So far, we've been really focused on looking at mechanisms and drawing them, but I want us to look at this. So he skips here, right? Steps 1 through 6, because these are analogous to equations 19 through 20, right? So you can go back and look at the imine formation in equations 19 through 20 on in previous screencast and previously in your notes, and you should be able to go from this to this. And I would suggest doing that, making sure you understand the mechanism and going here. Okay, so sometimes you're going to see shortcuts like this for things that are already known or things that are well known. But if you were asked to draw the mechanism, you would be expected to show these steps. Okay, and so now we have this result. It's a hydrazone. Now, a hydrazone is characterized by a CNNH2 group here. Okay, so this group here is called a hydrazone. Okay. And then the first 4 steps that occur after the hydrazone has formed, this step 7, 8, 9, and 10, right, serve to remove 2 protons from the remaining NH2 groups and add 2 protons to what was originally the carbonyl carbon. Okay, so notice in step 7 that the OH here comes in and grabs this proton. So another way to say that is it deprotonates the NH2 group. OH, I want you to notice, is not normally a strong enough base to do this, but what happens here is the resulting conjugate base is stabilized by resonance. And so that helps this reaction push forward. It's also stabilized by some inductive effects as well. And that just involves this adjacent NH nitrogen atom that's electron withdrawing. Then, right, there's a proton transfer. Okay, so these electrons come here and those electrons go there. And we reach an E2 step. Now, there's a few interesting things about this E2 step that you want to note. First, the proton and the leaving group are removed from adjacent nitrogen atoms. Okay, now, so that means that when we come here, right, we see that this is going to come and grab that hydrogen, and those electrons are going to go there, and then these electrons are going to go here. The reason that's peculiar is normally we see them on adjacent carbon atoms. Okay, so what we're seeing is that similar chemistry but with nitrogen atoms. Second, the thing that's kind of interesting here is that the leaving group's quite poor. A negative charge becomes localized on this carbon atom. Normally, and what we've learned so far is that this would prevent an E2 reaction from occurring, but the formation of nitrogen gas is a huge driving force because nitrogen gas is super stable, but it also leaves the system once it's formed, right? So this nitrogen gas here is super stable, and then it also leaves the system, right? And so this is Le Chatelier's principle in effect, because what happens is, right, this N2 is leaving the system, so we're decreasing the concentration of this N2, and so the reaction continues to shift this way, right? And so that's the driving force to push this reaction forward. And so it makes this overall reaction irreversible, right? Which also helps drive the formation of the products. It's a super cool reaction. I love that it has Le Chatelier's principle. I love that nitrogen gas is produced. Super, super cool. So the Wolff-Kishner, when you do it, is carried out in two sequential steps, right? First, what we see is that the hydrazone forms under mildly acidic conditions, and then the hydrazone reacts to form the methylene group under basic conditions. So you would end up with kind of this workup in the middle. So conveniently, though, the hydrazone can be formed under basic conditions too. So what we see then is that the Wolff-Kishner reductions can be carried out in a single step just by treating an aldehyde or ketone with hydrazine, right, which is right here, okay, under strongly basic conditions with a high temperature. So this is, again, an improvement over the previous reaction where we kind of had a workup in the middle where you can make this all a one-step reaction by staying here in some basic conditions. And so again, organic chemists are continually working on improving conditions, making reactions faster, making product yields better. So in this section, so we're kind of like hanging out here in amines, right? And in a previous screencast, we talked about like this hydrolysis of acetyls and imines. But nitriles, right? And I just want to remind you that nitriles have this R group with a carbon and a triple bond to a nitrogen, also can undergo hydrolysis. So we have an example, two examples shown here, okay? And so what you see here is the treatment of a hydrolysis either under acidic, right, or basic conditions can produce a primary amide. Oh, I was like, I've gotten lost. I was in the wrong place. Primary amide. Right here. Okay. And so to isolate that amide, the reaction has to be like watched very carefully. So this is a little bit delicate because it can easily undergo further hydrolysis to produce a carboxylic acid. So if you were doing this in the lab, you'd want to make sure that it didn't go on for too long. You'd want to look for the exact right reaction conditions so that you don't produce, if you're aiming to produce the amide, you don't want to go on and produce the carboxylic acid or the deprotonated carbonyl group, okay? So let's look at the mechanism for acid hydrolysis of nitriles. So let's start by drawing our reactants here. So there's our benzene ring. Right? And there's our nitrile trial group. And the very first step here is a proton transfer, and this is in acidic conditions. So we are going to use the acid here. Right? And what we see happening is these electrons come and they grab that proton, and then these electrons go back on the oxygen. So this is the product that we get. Right, where these carbons are going to come in here, and those electrons are going to go on the nitrogen. So now, Cl still there. Oh, I left out our Cl, right? Our Cl is still there. The carbon's here. Right. And then we undergo a proton transfer. With a water. Okay, and so with a proton transfer with water, these electrons come up, they grab that proton, those electrons go back on the oxygen. Right, and then we come in here, and these electrons go here, and those electrons go back on the oxygen. And then, hold on, I'm just double checking my structures to make sure. Yep, I'm just counting. I'm going back and forth and counting. Did not put proton transfer here. Right? And so right? What we see happen, oh, and I left off, hold on. I've done something strange as I've been thinking through this. This does not have a positive charge because it was deprotonated in the previous step, right? So it should have 2 electron groups on it. Okay, I'm just double checking. Once we get into these kind of wickedy wild mechanisms, I really like to make sure I'm double checking because it's so easy to lose an atom. So that's something you want to make sure you're double checking as well. So these electrons are going to come in here, and then these electrons are going to flop down here to make a double bond, right? And then that makes and pushes these electrons here onto the nitrogen. Now, so that's a proton transfer step. Again, we're looking back and forth and we're following our arrows to see what's going on, right? And there we are. So we formed our amide, right? And now we also have H3O plus as well running around. Notice that we've got 5 elementary steps here, and the only step that's not a proton transfer is the nucleophilic addition step in step 2. The 4 proton transfer steps add protons to the nitrogen and then remove them from the oxygen. So I want to point out no strongly basic species appear. No strongly basic species appear here, right? And so in this mechanism, and that's just really the necessary conditions for the reaction to take place under the acidic conditions, right? So we're staying here with acids. Now, remember, we can also do this on bases too. So I want us to look at that mechanism as well. And so the first step here is a nucleophilic addition step. And we're starting with a base, and so of course we're going to start with this mark of the OH minus here. And so what happens with the OH minus is these electrons come in and they attack that carbon, and then these electrons go up to the nitrogen, right? And so what we look at here is there's an oxygen, right? And then I counted 1, 2, 3 over. We've got our carbon, and we've attached the OH there. So we're going to show the electrons there, and then we're going to go down to the nitrogen. We're going to show the electrons here with a negative charge. Then we're going to undergo a proton transfer step where these nitrogen atoms come up and attack here, and then these electrons go onto there, okay? So then right? And I just had a misstep there. There should not be a dot there, right? It was just because I don't want us to confuse that and think there's an extra electron there. All right, so now we have this OH minus hanging around, and he's going to come in and he's going to deprotonate this oxygen, right? And what's going to happen is these electrons are going to come down here to make a double bond. Then these electrons are going to go onto the nitrogen in a proton transfer step. Right? And so when we look at that, right, we end up with another proton transfer step here, right, where the nitrogen grabs one more oxygen, and I left that negative charge off of that nitrogen, so don't forget that. And these electrons are going to go back on the oxygen. And so now we have right, our primary amide, and then an OH minus. Right? So I want you to see some comparisons here to the previous mechanism. The only step that's not a proton transfer is the nucleophilic addition step, and that's in step 1. And then similar to the previous mechanism, the proton transfer steps here are really going to add protons to the nitrogen and remove them from the oxygen, and remove one from the oxygen in this case. And so because the reaction takes place under basic conditions, right, there are no strongly acidic species, right? So make sure that you are watching out for if you are in basic conditions, we shouldn't have any acidic species, and then strongly acidic species. And then if you're in acidic conditions, you should not have any strongly basic species.